Hi, my name's Andrew McLaren, and I want to help you with molecular orbitals and their fill order, which can be a bit different for different atoms. And I've got in this video a really nice way of memorizing this that I generated using AI. So I have a whole separate video on how I generated these images. But this works really, really nicely. I've used it with a couple students I tutor, and they always remember the exception. So we're going to, in this video, go over why this is important in terms of solving some of these problems, like knowing this exception is important for para and diamagnetism. We'll talk about more about that in a minute. Then we'll talk about the trend, and then my trick that I've generated, and a more sciencey explanation as to why this is happening in this video. So by the end, you should be able to know the exceptions and then also be able to think about how that applies to para and diamagnetism. So depending on the class, your teacher might give you this to fill in. And if they have, you probably don't need to memorize the exceptions. And I've seen some teachers will be like, here's the figure, just use the figure. But sometimes they're like, no, you need to make it from scratch. So if I'm looking at this, I see two carbons and they have their atomic orbitals that I've got in blue. And then this is the molecular orbitals when you kind of put them together and you're trying to figure out how they're bonding and antibonding. And you can see that if I am doing this with the correct thing for carbon, which is the exception, the pi's you do first before the sigma, these should be all paired up. And if they're all paired up, it should be diamagnetic, but you might fill this in incorrectly if you were assuming that these are actually the regular fill order, and then you can see that we have these unpaired electrons in there. So it's important to know the exception because you might misidentify something as like paramagnetic when it really should have been diamagnetic or vice versa. And these are very typical problems that you would have where you have to use molecular orbital theory. And that comes into play, that exception, into quite a few problems. So I've got another one right here. This is the C+2, so it's got one less electron. And so it looks very, very similar, but we want to fill that in appropriately in the correct spot. Now, it wouldn't be such a big deal for like this one if you were to use the wrong molecular orbital. It would still kind of work out because you would end up having like 1, 2, and 3. So there's kind of an unpaired one in both of these. So it does work out occasionally if you use the wrong one, but you want to be careful. So to really make sure we're using the correct fill order, we're going to talk about the trend and the trick to memorize this. So when we're talking about this, there's often a big focus on the B, C, and the N because they have like the exception to the fill order. But it's important to note that the normal fill order is kind of what we're seeing here with the oxygen, the fluorine, and the neon. That's what we would call the normal fill order. And you can see that in that case, that the what we have with the sigma in relationship to the pi is slightly different. So we've got the 2 pi here and 2 pi there, and you can see for like C and N and B that you're going to be filling in your pi's before your sigma, so that relates to the trick. So what's a little bit weird if you're looking closely is like, what's going on with these? Well, these should be empty. So you don't usually fill those with electrons anyways when you're doing like lithium or beryllium. Because they don't have enough electrons, they're not going to fill those orbitals. And so you don't even worry about filling those in. So the trick is that you really need to worry about B, C, and N and having those filling in the sigmas in a different order than like oxygen and fluorine and neon, which would have electrons present in those orbitals if we're talking about something that's like neutrally charged. Fluorine is contributing, 7 valence electrons each. So that's going to fill these up quite a bit. Whereas like lithium, it's only got, I think, 1 valence electron each. So it doesn't even get anywhere close to this. So that's the trend visualized, and you can kind of see how this fill order is different. for things that actually have this stuff in, where we've got the BCN and then the OF in the neon. Interestingly enough, the fill order, you typically only do this for like the second energy level. You could do this for like chlorine, and like sulfur and all those other things. They do have a similar fill order, but they typically don't do that. They do have a similar exception where it's like, okay, the thing underneath carbon and boron have a similar trend where you want to have that that sigma bond actually be a higher energy level. And we'll talk about why in the explanation. So if you're like, why is that going on? I'll get to that soon. But the more important thing is just knowing which one is for most students. So to create this, I used a couple different AIs to help me come up with some lists. I'll go over exactly how that works in a separate video, but I knew that I wanted a mnemonic that had B, C, and N in it. And I wanted to have this to be something related to like 2 pi. And I thought that that sounded kind of like the word pi, and that there might be something where we can kind of tie in all these words together. In the end, I did come up with a big crunchy nibble. And I was thinking of that relating to this like idea of pie and like eating, or maybe being at like a diner or a restaurant or something like that. And so I was thinking, what if there's a diner that has a motto like the BCN, like that's their thing that they have in their advertising, that every meal starts with a big crunchy nibble of 2 pi pie. So that's the mnemonic. Every meal starts with and I'm just going to do BCN of 2 pi pi at Moe's diner. So we're going to molecular orbitals diner. Get it, Moe's? And so this helps you kind of remember how all this stuff relates. Now, just saying that is a nice start, but it's not perfect. So you may remember the image that I had at the beginning of the video. I have a number of variants that I've made with AI trying to see what Moe's might actually look like. And so we've got like an image right here, and they've got like pizza pies as like the pie. I really like the Moe's in the background. The people are all weird, but like what's more important is that you've got Moe's being some sort of pie, pizza pie kind of place. And that's like something that they serve with every meal. This particular image I enjoy because look at this guy's head. He's got pizza on his head. There's definitely the faces are a little weird, but I like how also these two people each have like a whole pie to eat themselves. It's pretty awesome. In any case, that's the trick that you can use to remember that you've got to do 2 pi first when you're at the BCN, or boron, carbon, and nitrogen. If I haven't made that clear, these are related to those 3 atoms. Which have like the fill order exception, although they kind of do match if you think about like lithium and beryllium have similar things. So we'll talk about why in just a second. So to help you really understand what's going on here, we really want to draw out these atoms a little bit. So if we've got like lithium attached to another lithium, there is a bond between these. And that bond is containing 2 electrons. So this bond is taking up some space. If we're talking about something like nitrogen now, it does have a bond in the center here, but this is maybe like the 1 sigma bond, and this is taking up space, which is gonna cause us an issue because in addition to that, we've got another pi orbital present. So if we have our 1 sigma, we're also going to have a 2 sigma that also has 2 electrons, and these are going to interfere with each other. So if we can have that interference go down, then 2 pi is going to be stable. So if these things are interfering, that means that this sigma, the second sigma, is unstable, which is kind of why we're having these things be high up here, where we've got this unstable thing due to that interaction with its first sigma electrons. Now, if we make this a bit stronger of an atom, if it's something like oxygen bound with another oxygen, this sigma ends up being really small. The area that this takes up between these two atoms ends up being smaller, and there's less interference. Because these have more like Z effective or like a larger nucleus, that means that these electrons are getting pulled into like a tighter area, and so they don't interfere so much with the 2 pi. And so this being smaller means there's less interference with the next energy level that's present. So if we're talking about that 2 pi now, it is comparable, but a lot less interference. So if you're talking about things that are stronger, they have like a bigger nucleus, like oxygen, fluorine, and neon, then you're going to see something where we have a smaller area for this sigma, meaning that it's getting more stability due to the fact that it's getting held in a little bit tighter. That's the main idea. It's a little bit more complicated, like with everything in chemistry, but that's the main idea on why this sigma is unstable for these atoms that aren't quite as big, and then it becomes more stable once we have a bigger Z effective. I did briefly mention like what was going on with like chlorine or like sulfur. These things are going to follow the same trend because now it's a question of, is this thing being held in tighter relative to the third energy level? And there's going to be some interference from the second and first energy level, commonly affecting the next one up, like how we're seeing here, where one is affecting the second energy level stability. So like that third pi is going to be pretty unstable at first, but then it's going to become more stable as it goes closer to the right side of the periodic table for that third energy level. So like chlorine is going to have a relatively low sigma thing, kind of like what we're seeing here on this periodic trend. Though you're typically just going to stay in the second energy level, like with lithium, neon, oxygen when you're doing this stuff. You don't typically see stuff with the third or the fourth energy level. All right, I think that's that. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.